In this lecture, we're going to cover Chapter 5 and Chapter 6, the chemical bonding and nomenclature, and the shape of atoms and molecules. So first, let's look at ionic bonding. There are trends in electron motion. Metals tend to lose electrons, and nonmetals tend to gain the electrons. Here's an example. When a sodium atom, which is group 1, reacts with a chlorine atom in group 7, each sodium atom loses an electron, and each chlorine atom gains an electron. Ionic compounds are formed by the attraction of ions with opposite charges. The ions stack positive next to negative, just like a magnet. Ions are very strongly stuck together. This is called electrostatic force. You can see the positively charged sodium with a negatively charged chlorine that will attract and stick together in this manner. Electrostatic forces are governed by Coulomb's law. The strength of the attraction is as follows. Since Q1 is negative and Q2 is positive, the electrostatic force is negative. Since Q1 and Q2 are both negative, the electrostatic force would be positive, or repulsive in the second example. The smaller the distance and the larger the charges, the stronger the force holding oppositely charged ions together. So if we were to compare the forces of attraction in a sodium chloride to those in magnesium oxide, would the magnesium oxide forces be larger or smaller? Since the charges are larger in magnesium oxide, +2 and -2, the attractive forces would be larger. So ionic bonds are chemical bonds occurring between ions and opposing charges. They're present in ionic substances, and it forms extended three-dimensional lattices as a group of the ordering of ions. There's two types: crystalline, which is a material with a long-range, highly ordered lattice, you can see on the right, or amorphous, which is overall order and the extended no overall order. It's just, all over the place. So we'll look at molecules. Molecules are a collection of atoms bound together. An example is oxygen gas, or O2. A molecular substance is a substance composed of distinct molecules. It exhibits distinct individual groupings of atoms. For example, a molecular compound composes of 2 or more types of elements. Example, CH4 and H2O. Elemental substances are only one type of element, O2, Cl2, or I2. Okay, one element, multiple of one element. So the molecular properties are not an average of the properties of the individual atoms that make up the compound. We have a glucose molecule here. Natural sugars in the honey are broken down to glucose within the body. So would you expect the following to have a nearly identical property, H2O and H2O2? Okay, we got water and hydrogen peroxide here. No, these molecules have different compositions, so they would exhibit different properties. Next, we'll talk about a covalent bond. Covalent bonds is bonding that occurs between electrons in one atom and the nucleus of another atom. In the H2 molecule, each electron is attracted to 2 nuclei. This results in electrons rotating around both of the nuclei. The electrons spend most of their time between them, although they spend some time in other places, as you can see in these pictures. There are a couple types of electrons in covalent bonding. You have the core electrons. These are almost never involved in bonding because of how close they are to the nucleus. Then we have those valence electrons that we talked about before. These are the electrons that are shared between the neighboring atoms, and they're responsible for that covalent bonding. Just a little reminder, the group number pertains to the number of valence electrons. For example, group 8 has 8 electrons. So here's some representations of a covalent bond using hydrogen. The line between two atoms denotes a covalent bond. So when we look at the energy of these bonds, bond formation releases energy and bond breaking takes energy. It takes a lot of energy to take a salt molecule and pull it apart, but it's really easy to get them to stick together. So chemists count shared electrons as being in both atoms. Here's a hydrogen atom. Each atom owns 1 electron. In an H2 molecule, each atom owns 2 electrons. Covalent compounds do follow that octet rule. Atoms in a molecule share electrons to obtain 8 valence electrons. Consider a carbon atom. This contains 4 valence electrons in a neutral atom. It must form 4 covalent bonds to reach its octet of 8. So the carbon atom seen here has 4 valence electrons, so it has an unfilled shell. It wants 8, right? So 4 hydrogen atoms come in, and they're all able to connect, making 8. This leads us to the CH4 molecule. By sharing electrons, each atom now has a pretty filled shell. So here's another picture of how this works. The number of covalent bonds nonmetals usually form. So hydrogen has 1 valence electron, and it needs 1 to achieve the octet rule. It's a duet for hydrogen. These guys have 4. Okay, this is the number of bonds an atom of the element usually forms, 4. Group 5 forms 3, group 6, 2, and group 7, 1. Those are the number of electrons needed to achieve octet in those groups. Predict the compounds that form between the following: carbon and chlorine, and phosphorus and hydrogen. I encourage you to pause the lecture here, use your periodic table and the octet rule to see if you can see how many would be needed of each to form a molecule. Push play when you're ready to see the answer. So with carbon and chlorine, the carbon needs to form 4 bonds, and each chlorine forms 1 bond, making the CCl4. Phosphorus and hydrogen, the phosphorus has 5 valence electrons, so it will form 3 more bonds, while hydrogen forms 1, making the formula pH3. Looking at Lewis dot diagrams. These are kind of nice because you can actually see the amount of valence electrons around it by using dots. There's 2 parts to this. The element symbol, as you can see if we look at lithium up here, and the number of dots corresponds to the number of valence electrons. So the electron pairs show 2, and an unpaired electron would be 1. Electron pairs are paired electrons. There's 2 electrons usually on one side. You wouldn't have 3. The unpaired is where there's only 1. Okay, you put 2 on each side, 4 sides, octet, right? So the octet rule in the Lewis dot structures, the elemental fluorine has 7 dots around the fluorine, as you can see here. In diatomic fluorine, each atom shares 1 electron to form octets. So here's the 2 fluorine atoms. Each atom has 7 valence electrons. These 2 unpaired guys pair up to form a covalent bond. Here's how we would draw some more molecules using the electron dot structures. We have these 3 fluorines fit nicely on these 3 open sides of this nitrogen. Here we've got carbon with these 4 hydrogens coming in to create a pretty little octet rule as well. Here's NF3 redrawn with lines instead of dots for bonding pairs. So if you have 2 pairs bound to 2 pairs, you can draw a line. So how many valence electrons are in NF3? How many bonding pairs are there? How many non-bonding pairs are there? Take a second to pause the video, come back and look at the answer when you're ready to see if you're right. There are 26 valence electrons. If you count around, 1, 2, 3, 4, 5, 6. Okay, count all the way around, you're going to find 26. How many bonding pairs? You can see we got 3 sets of bonding pairs. And how many non-bonding pairs? There's 10. Okay, going around the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How about having multiple bonds? If we have two atoms that share more than one pair of electrons with each other, note that each oxygen only has 7 valence electrons. Okay? Each oxygen atom has 6 valence electrons, and each oxygen atom now has 7 by connecting. Each atom still has 1 unpaired electron left. Can share these to gain an octet for each atom. The formation of a double bond or 4 shared electrons is seen here. Each oxygen atom has 7 valence electrons, and each oxygen atom has 8 valence electrons, the double bond. We have 3 types: a single bond, which is 1 pair, double bond is 2 pairs, and a triple bond is 3 pairs. Try to draw the dot diagram for carbon dioxide, which is CO2. Pause the video here, use your periodic table and the information you've been given to see if you can draw CO2, and play the video when you're ready to see the answer. Okay, as you can see, our oxygen, 2 oxygens connect to a carbon, and we can actually have 2 double bonds. So the steps to draw a dot diagram: determine the total number of valence electrons, connect the atoms with a single bond, place the remaining electrons as lone pairs, first on the terminal atoms and then in the central one. If each atom does not have an octet, change lone pairs to bonding pairs. There we go. Next, we're going to look at polyatomic ions. These are ions made up of multiple atoms. You need to adjust the number of valence electrons to account for the ion's charge. NH4 would have 1 fewer electron as a result of the +1 charge. NO3 would have 1 extra electron as a result of the -1 charge. So electronegativity is the numerical rating of an atom's ability to attract shared electrons. It determines if electrons are shared or transferred when a bond is formed. The greater the electronegativity value, the more likely electrons will be drawn to an atom. So 2 atoms with identical electronegativity result in a pure covalent bond. But if we have different electronegativities, this will lead to a polar covalent bond, having unequal electron sharing. A negative is a partially negative charge, and the positive is a partially positive charge, as shown here. Okay, you can see this is a nice picture down in the bottom because the negative and the positive are shown unequally. So in the electronegativity difference, the larger the electronegativity, the greater the polarity of a bond. Okay, we increase in polarity as we move this direction. Carbon, or CCl4 would not be polar due to having a similar electronegativity when we look at the periodic table. Here are some common chemical names. So sometimes we have to name these, and they have some names that maybe don't sound exactly like it looks. For example, H2O would want to be like hydrogen peroxide, or, dihydrogen oxide would be water. So H2O. NH3 is ammonia. Hg2Cl2 is calomel. So there's different common chemical names, but we're going to look at the standard names. So binary compound naming refers to having names with 2 elements. We have binary ionic compounds composed of a metal and a nonmetal, and binary covalent compounds, which are composed of 2 nonmetals or metalloids. You can see we have the ionic compounds and the covalent compounds shown on this chart. When we name these, the metal forms the cation, which is written as the elemental name. The nonmetal forms the anion. Add the suffix "-ide" to the elemental name. So here we got Na2S, which is sodium sulfide, MgCl2, which is magnesium chloride, Al2O3, aluminum oxide, and Li3N, which is lithium nitride. Traditional metals have multiple charges in some cases. We use Roman numerals to show their charge. For example, iron 2 uses Fe2 and Cl-. This is ferrous chloride. Okay, usually having 2 is us, 2 of us. FeCl3, ferric chloride, 3 is icky. Okay, 2 of us, 3 of it. It's just a way to memorize it, not that it's really icky. So try to name the compound TiCl4. Pause the video when you're ready to move on and get the answer. Push play. Cl is in group 7A, so it must gain 1 electron to become a Cl-. Titanium must be +4 to balance the 4 chloride ions. The name is titanium 4 chloride. Here's a chart to help you name your binary ionic compounds that we just reviewed. So naming binary covalent compounds uses prefixes to indicate how many atoms of each type are present. Mono, di, tri, tetra, penta, hexa, hepta, octo, nona, deca. Those are the Greek prefixes to determine how many of an atom are present. When we have both metals and nonmetals, the less electronegative element is treated like a metal. It is the first in the formula, and it carries the name. The more electronegative element has the suffix "ide" and is appended to the name. For example, HCl is hydrogen chloride. Here is a chart to help you name binary covalent compounds. Here's some examples of polyatomic ions. NH4 is ammonium, CH3CO2 is acetate or phosphate, is acetate, CN, cyanide, NO2 is nitrate, NO3 is nitrate. That's important to make note of. Just like SO3 is sulfite and SO4 is sulfate. And some other examples. Oxyanions are a nonmetal plus 1 or more oxygen atom. Ite denotes fewer oxygen atoms, and 8 is a greater number. As you can see here, sulfite has 3, sulfate is 4. Then sometimes we name acids. An acid dissolves in water and produces hydrogen ions. So does the acid contain oxygen? If no, it's a simple acid. If yes, it's an oxyacid. Acids with no oxygen atoms use the prefix hydro. Add the suffix "ic" to the root name of the nonmetal. Finally, add the word acid. Hydrofluoric acid, hydrochloric acid, hydrosulfuric acid. Acids containing an oxygen atom are different. These are a class of compounds called oxyacids. Look at the polyatomic ion in the formula. If the ion name ends in "ate," the suffix changes to "ic." If the ion name ends in "ite," the suffix changes to "us." So here's a sulfate ion, sulfuric acid. They have nitric acid, sulfurous acid, and nitrous acid. Here's a flowchart to help you name those chemical compounds. Try to name the following acids based on what we just learned. Pause the video here, use the resources in your PowerPoint, and see if you can figure out the names. Push play when you're ready for the answer. Hydroiodic acid, chlorous acid, and chloric acid. Moving on to Chapter 6, we're going to briefly touch on the shape of molecules. There are limits to dot diagrams. They only show the connectivity. They don't show the three-dimensional shapes. These shapes define the chemical properties of the molecule. First, let's look at our diagram. So when you're looking at the shape and how a molecule looks, you can see it in a 3D manner even though it's on paper. This is called a wedge dash diagram. In the wedge, it means it comes forward out of the plane of the paper. If it's got dashes, it goes back out of the paper. And if it's a straight line, it is in the plane of the paper. All right, so valence shell electron pair repulsion theory, VSEPR. This is a model used to predict the three-dimensional shapes of molecules. It's based on how negative charges on electrons repel one another. Simply put, electrons move as far apart from each other as possible. Here's an example. So if there's just two, you're going to have a bond angle of 180. It's pretty linear, as seen by carbon dioxide, CO2. If you have 3, all the bond angles are 120 degrees, such as sulfur trioxide. If you have 4, all the bond angles be 109.5, or tetrahedral. When we look at molecular polarity, H2 is a non-polar molecule. It does not contain areas of differing charges. Although HF is a polar molecule, it contains polar covalent bonds. Electrons spend more time on the side of the bond. The larger the difference in electronegativity, the more polarity a binary molecule exhibits. So the difference in electronegativity between hydrogen and chlorine is 2.1 and 3.0 is 0.9. There's a larger difference in electronegativity between hydrogen and fluorine. So an arrow can be drawn with the tail at the plus end and the head at the minus end. The longer the arrow is, the greater the polarity is. A shorter dipole moment vector means less polar bond. A longer dipole moment vector means a more polar bond. So molecular dipole moment is associated with the entire molecule. When multiple bonds are present, the following conditions must be met. At least one polar must be polar covalent, and the dipoles must not cancel out. Water is polar, whereas C2Cl2 is nonpolar, as you can see here. Dipole forces, or dipole-dipole forces, cause the ordering of polar molecules next to each other. The positive portion of the molecule attracts to the negative portion of another, as you can see in these two water molecules. This attraction is an intermolecular force. Here's the process of going from molecular formula to molecular polarity.